Let's see, I think when class stopped Tuesday, we were right here. We'd introduced this concept of critical point. A critical point for a function, critical number, is an x value where the derivative either is 0 or does not exist. And we were working on this problem when we ran out of time. Suppose f is x cubed minus x on this interval from 0 to 4. And they ask us to find all the critical numbers two ways. First, to look for them on Desmos, and second, to use calculus to see where they are. So I'm going to start with the calculus approach. We said f prime was 3x squared minus 1. So the first thing to notice is this exists for all real numbers x. It has no denominator that could be 0. It's got no radical that might be radicand that might be negative. I can take any real number and square it, multiply the result by 3, subtract 1 from that. So there are no critical numbers of the kind where the derivative doesn't exist. So let's see if there's a place where the derivative equals 0. And this is a nice equation because x only appears in one place. So I just have to undo the stuff that's happening to x. I'll add 1 to both sides. Now the last thing happening on this side is multiplication by 3. So I'll divide by 3. I'm finding I get rid of the squaring by taking the square root of both sides. There are actually two solutions to an equation that says x squared equals something positive. A positive answer and a negative answer. That's why when we take square roots of both sides, we always say you have to take plus or minus the square root. Right? This symbol without the plus or minus always stands for the positive root. So putting a plus or minus means the positive root or the negative root. On our interval, x can't be negative. So the only critical number on this interval is, I guess they sometimes call it c. It's an x value. It's positive the square root of 1/3. And let's see how that looks when I look at the graph on Desmos. I was gonna let you do this one, but I think this is kind of a tricky one. I'm gonna get you started here and maybe get you finished too. I want to find the critical numbers for this guy. And I think it's a little easier if instead of using the product rule, if I distribute this through here before differentiating. So I'll rewrite f. Well, when I multiply this x to the 4/5 times x to the 1, that's x to the 1 4/5, also known as 9/5, minus 2 times x to the 4/5. My handwriting's not the best there. Here, let's take the derivative. So I'll have 9/5 x to the 4/5. 9/5 minus 1 is 4/5 again. And then minus 4/5 times 2 is 8/5. X to the negative 1/5. So is there any place where that doesn't exist? Well, the denominator of 5 in these radicals means that I'm taking a fifth root. And I can take the fifth root of any number, so that's not a problem. But the negative exponent means this. There's a root x, there's a fifth root of x in the denominator. So I can't let x equal 0. X equals 0 is a place where the derivative doesn't exist. Notice that in the function, there are no negative exponents, so the function does exist at x equals 0. In fact, the function looks like it's defined for all real numbers. It doesn't have any denominators. There's no negative exponent, so x isn't in the denominator. Um, and this fifth root can be calculated for any x and then raised to the fourth power or raised to the ninth power as it is there. So x equals 0 is a critical point, a place where the derivative doesn't exist. Let's set the derivative equal to 0 and solve to see if there are any other x's. I'm going to multiply both sides by 5 to get rid of the fraction. And 0 times 5 is still 0. Why don't we add this term over there? So now there's a positive on both sides. And I'm going to multiply both sides. I'm going to multiply both sides by x to the positive 1/5. Why would I do that? Because when I multiply these two powers of x, the exponents add. And 1/5 plus negative 1/5 is 0. X to the 0 is just 1. So that's 8 equals 9 times. When I multiply these powers of x, these exponents add. So this is x to the 1. So for f prime to be 0, 8 has to be 9x. So x is 8/9. Yeah, I guess I did more than just started on that. But here, let's take a look at this on Desmos. Well, why do we care about critical numbers? It's because of this idea. Where could the max and min of a function occur? And critical numbers are important because I'll draw a couple of examples. There's A and B. Here's a nice continuous function, and it's got a maximum there and a minimum there. Let's draw another continuous function. I made that one have a little cusp there where the derivative failed to exist. I'll try to draw this one so the derivative exists everywhere. It's okay, I guess so. Let's say that's A and B. One more. How about? So the thing that I see in all of these pictures is that the minimum or maximum can appear at an endpoint, like it did. This is kind of a tie, but one of the minimum seems to be one of these two altitudes. I can't quite tell which. The minimum of this function seems to be that altitude. So the minimum or the maximum could appear at an endpoint. I didn't show you a maximum, but here's one. Now the maximum occurs at an endpoint. But if it doesn't occur at an endpoint, it occurs at a place like this one, or that one, or this one. Seems to be a max there, seems to be a minimum there. And what these all have in common is that they are critical numbers, places where the derivative is 0, because there's a horizontal tangent here, or over here. or undefined, like at this sharp point there and there. So we're looking for critical numbers because they're the only places where where the function might have a max or min. And if I look back at these two functions we graphed before, well, let's look at this one again. On this interval, I have a nice continuous function, so it should be differentiable. Here, let's do this. I've gone to page 75. What this picture shows us is a way to find the max and min of any continuous function on a closed interval. Closed and bounded means neither endpoint equals infinity. And the method is to find the critical numbers of f, and you check the value at all the critical numbers that appear inside the interval, and you check the value of the function at the endpoints. And the max and min must be among those values you calculated, the value of the function at the critical numbers and the values of the function at the endpoints. So for instance, in this guy, they want me to find the absolute extrema for f on this interval 0 to 5, and then use calculus techniques to confirm our answer. So I've got a graph of the function over here. So the derivative is the derivative is 4 minus 2x. Is there any place where that doesn't exist? No, I can multiply any number by 2 and subtract that from 4. So there are no critical numbers of the type where, sorry, this is f prime. There are no critical numbers of the type where f prime doesn't exist. But let's set f equal to 0, and I'll bring the 2x over to this side by adding 2x to both sides, and then divide by 2. So there's the only critical point, the only critical number. My 2 looks like a z. And that's consistent with the picture that we saw here in Desmos. According to this rule, I should find the max and min if I just calculated the function 12 plus 4x minus x squared at these three numbers, at the endpoints and then at the critical number. Let's just try that here. Here, you calculate these at 0, and at 2, and at 5. Pause the video for a second while you calculate those. Have you paused it yet? We'll pause the video for a second and calculate those three values. I'll start back up in a sec. Are you ready? I'm going to show you what I calculated F to be at these. I calculated it to be 12, 16, and 7. 16 at the critical number in the interior of the interval. 2, I'd say, is in the interior, it's in between the two endpoints. And it looks like the smallest value is 7. It looks like the largest value is 16 and the smallest is 7. And that's consistent. Let's try this next problem. You can go to Desmos and plot this function from -2 to 3. And I'll give you a Desmos clue. I don't know if you noticed this, but you can make homework here, this cubic polynomial on that interval. And you should see some extreme points. They'll be at critical points or at the end points. And then use calculus to calculate the derivative, set it equal to 0, and learn those critical values. Then you can just check by hand that when you differentiate f at the two endpoints and at the critical numbers you find, that the max and min are consistent with the ones that you find in the picture on Desmos. All right, you stop the video and do that. And when you start it again, I'll show you the answer. All right, we're back. I'm going to show you what I calculated when I did that problem. I found the derivative was 6x squared minus 6x minus 12. That exists for all real numbers x, so there are no critical numbers of the kind that cause the derivative to be non-existent. I set it equal to 0, and when I set something equal to 0, it's always nice if I can factor this thing. So I factored out the 6, and then I used backwards FOIL to factor this quadratic polynomial here. Then I used the fact that if the product of three numbers equals 0, it has to be that one or the other was 0. Well, 6 can't equal 0. So for this to equal 0, x minus 2 had to be 0, or x plus 1 had to be 0. That's at 2, that's at x equals 2 and x equals -1. I calculated f, or rather I calculated f at those two critical numbers, x equals -1 and 2, and at the endpoints, -2 and 3, and I found it to be -3, -8, -19, 8. The order doesn't matter. The thing is the max and min of the function has to be in this list. That must be the absolute max because it's the largest of these four numbers. And that's got to be the absolute min because it's the smallest of these four function values. And sure enough, when I look on Desmos, let me try one more function we'll do together. This one, we already figured this out. I think I calculated the critical numbers earlier. What were they? That looks familiar. Oh, the critical numbers were 0 because the function's derivative didn't exist at 0, and 8/9. If I calculated the function at the endpoints, -3 and 5, and at the critical numbers, 0 and 8/9, the max and min has to be in among these 4 function values. Let's see what those are. So I've got the local max. I'll find the absolute max and min. The absolute max and min must be in this list. Since that's the largest of these 4 numbers, that has to be the absolute max of this function. And since -12.04 is the smallest, that must be the absolute min. And that's consistent with the graph that I saw before. The algebra is easier on this guy. Let's do the same thing for this function on that interval. And before you go using the quotient rule, ask yourself, how can you rewrite 1 over x to make differentiation easier? So you try that with your team, and I'll show you the answers when you come back. All right, I'm back. Here, let me show you what I did. In order to make differentiation easier, I wrote this as x plus x to the -1. The derivative is 1 minus x to the -2 using the power rule. So these negative exponents mean that this function doesn't exist at x equals 0. I don't think that should be called, I wouldn't call that a critical point though. I mean, I wouldn't penalize you if you did, but I don't think it's a critical number because the function itself isn't defined at that x value. So this couldn't, x equals 0 is not a place where this function has a max or a min because the function is not defined there. So I guess I'd say that 0 is not a critical point. So I'll set f prime equal to 0 and solve for x. I added the x to the -2 over here. And sometimes I think it's easier to write this without negative exponents. This just means 1 over x squared is 1. Okay, I'll multiply both sides by x squared. Maybe I went a long way to get here, but x squared is 1. What are the solutions? Well, x squared is 1 only when x is -1 or 1. Furthermore, this isn't in our interval, -1. So that's the only critical number in our interval. So I evaluated the function at the 2 endpoints of the interval from 0.2, that's 1/5, and 4, and at 1. I calculated the values to be 5.2 and 2.0 and 4.25. Well, the minimum's got to be the 2 that I see there, and the maximum must be that 5.2. And when I look at the graph, I promise